So for this last talk, I'm going to talk about multitask learning. Not so much in general, but for a specific purpose, which is to have integrated perception. What do I mean by that? Perception, when I talk about perception, I mean like sensing the real world, understanding the real world. So perception tasks can be, for example, if you from image, could be object detection, a sync classification, or depth estimation, things like that. So when someone wants to do perception for images, basically you want to do sync classification, so you train one model. If you solve it with machine learning, you train a model, and then you have a model that takes an image and gets you, oh, this is a scene in a street in a city. And then you want to do semantic segmentation, and then it says, okay, there is some trees here, there is the road here, there is a car, puts every pixel of one label, right? And you can do the object detection and depth estimation and odometry, and all of them, you train one model that specializes in doing that one task. That's how it's usually done. However, in the real world, we want to do all these tasks simultaneously. If you want to deploy an autonomous car that goes around on its own, you want to make sure that you know that you're in an urban street, and you want to make sure that you see which pixels belong to cars and which belong to road, and you want to make sure that you estimate the depth, and all of this at the same time, not now I do this and now I do that. So you need to use all these models that I showed before simultaneously. And if you guys have used deep learning, which is how you solve all these tasks lately, you probably know that this takes a lot of computing power, even for inference. And not only computing power, but like takes a lot of memory in the GPUs. So it's kind of hungry in terms of resources, right? Deep learning. And in the end, all these applications that you want to use in the real world for robotics or cars or phones, for example, you're going to deploy them in embedded systems in some way or another. Maybe some embedded systems that you have in a car are more powerful, but still, it's not like what you have in the cloud, right? So there is kind of this doesn't match. We need a lot of computing resources, but we don't have them in the system where we want to deploy it. So we need a solution that scales with a number of tasks, and the previous solution of having one model specializing for each doesn't really seem to scale that well. So the one solution is to have a multitask model. What does that mean? It's a model that takes an image, and as an output, it gives you an output for every single task that you define. So this might sound like, oh, how can you do that? You will have all the models integrated in one, but are they going to be like a lot of networks in parallel? Or so I'm going to try to explain that. Well, first I want to just define multitask learning, like the book definition. So it was defined in '97 by Vic Caruana, and it was defined as multitask learning is an approach to inductive transfer that improves generalization by using the domain information contained in the training signals of related tasks as an inductive bias. What does it mean? First, that when they thought about using multitask learning, they didn't think about using multitask learning to have smaller models, but they thought of using multitask learning to help their models improve their performance and be just better. How? By using the training signals of other tasks as a regularization, like you do L2 regularization or these kind of things. Multitask learning was thought as a regularization technique in the beginning. But that's great news. So not only it's smaller, but it also seems to improve the performance of your model if you do things properly. So we'll see later. So this is the first point about multitask learning that is like a good thing to have. So we have a shared representation, and by having the shared representation, we improve the generalization, and by having a shared representation, we also share the resources to compute it, which is why it's a smaller model, right? And after that, we have you can actually scale with this, because adding an extra task doesn't mean adding a whole new model with the whole new representation. It just takes this shared representation, this feature extraction part, and then you attach something to it, which will be smaller, because if you know, at least in the case of convolutional neural networks, which is what we use for all these vision tasks, the biggest part of the computation is in the first layers. So the first maybe like 5, well, depending on the architecture, but the first 5 to 5 layers, let's say, I think it was in VGG, for example, if you know what architecture that is, takes 75% of the, about 75% of the resources to compute. So if you add something after that, it's going to be very small in comparison to this. And after that, also a good point is, instead of having to train all these models separately, we train it once and we're done. So instead of training for deep tasks, we train it once. If everything is okay. So there are different ways of doing multitask learning. One is this, having this shared part and then different heads for each of the tasks. Another one I was saying would be to have this common part, not really common, but share stuff between one and the other. But this obviously doesn't really benefit us in the terms of having less computation. So I'm going to talk mainly about this one. For the third one, for example, it's like this one, but maybe you have some lower level tasks that you want to do, so you use features not that deep into the network. Any questions until here? Maybe I'm going too fast. Good. So, well, one intuition why this might work, or this works at all, is first, CNNs have been shown to be highly hierarchical. So the first layers are find edges in the images and things like that, and in the later part of the network, you have more like a higher level concepts, like faces of dogs and cats. I'm sure many of you have seen these images. And we have been using this in computer vision, deep learning for computer vision for some years now. As transfer learning, you train on typically ImageNet, and then you deploy it on you use those weights to train other tasks, something like this. So we have a network which was meant for image classification. We train it in ImageNet, and when it's trained, we drop the last layer that actually does the classification, and then transfer learning. Yay! We put another task on top, which is, in this case, object detection. This is SSD, if someone knows about object detection. Basically, you are taking these weights that you had trained before, you put them here, attach some extra layers, but very few in comparison, and you train again, but starting from these weights that you had already trained. And this has been shown to improve the results, make training faster, and it's like commonplace when doing deep learning in general. You can also do it for another task, on the segmentation. Question?
I was just worried about that single movement, which is like the hourglass.
It's some special kind of layer that there is in the SSD model. I think it does some kind of normalization of the magnitude of the activations. It's been a while since I checked it, but I think it's that. So this is FCN, for semantic segmentation, the first fully convolutional networks. Just same feature extractor in this case. As you see, we dropped a few extra layers. But if we do this and it works, why not just having this and have all output at the same time? So this is just a multitask network doing object detection and semantic segmentation. So this is the idea, very simple. Just take this common trunk that has been already pre-trained or not. In this case, if it has been, it will benefit, and then attach different heads for different tasks. That's it. Well, that's it. Now it comes the funny part. You have to train it. Well, okay. So this is just the same thing, but with less detail. But now I'm adding the loss, which doesn't it doesn't show. Okay, well, the loss is just weighted sum of the loss of each, like the joint loss on which you train is just the weighted sum of the losses of each of the tasks. But tell me,
how do you weigh the losses for the tasks?
Okay, so that's one of the biggest issues right now. Most people doing multitask learning, they have not even been aware that they were doing multitask learning. That's one of they can go into the common part at different places. Like one can, for example, we see here. This one goes in when you train this, the gradient will propagate into the network at different parts. So it makes sense that the losses will not have the same magnitude here or there.
So you have not locked the first step.
No. You can do that, but then it's not that much fun. Then it's like you're gonna the common part will not really benefit from having a multitask training, and the performance that you will get from a transfer learning perspective. There is some work on studying. Should you freeze the first part, not freeze the first part, freeze some layers, some others not? In the end, most people just don't freeze anything and just train everything again. Because if the training works properly, it will just adapt a bit better to whatever tasks you have, or not changing at all. One reason why people have done it, but no,
so a factor of 2 maximum. Anyways, I guess.
A factor of
2. Because usually do a forward pass.
Yeah, but if you would be freezing all the network, then it would be much faster. The training.
It might take longer to convert.
Well, assuming that it doesn't take long to convert. To do the same forward and backward passes. Anyway, so you have this loss, joint loss, where you sum different losses. And I was saying a lot of people don't put any actual value for that lot for the weight, so they just take 1 for all the different parts. Some other people tune it by hand, so another hyperparameter, great. And some other people have been studying exactly that problem, how to choose that hyperparameter. There is work. Well, I will show later one of them. Let me first talk about other challenges. That's one of them, which is that loss weighting. So I can start with that. The fact of not caring about those weights might mean that you have very different magnitudes for different losses. So everything can get a mess. One task will train, the other one will not. One will be very fast and start overfitting, while the other one's still starting to train, things like that. So the idea is that you want to balance these gradients, right? So all the tasks are equally important when doing the training. There is work by Kendall from Cambridge. Is he from Cambridge? Yeah, anyway, he used uncertainties to model these weights and find the proper weights for the training. And there is a recent unpublished work by Magic Leap that basically they do something kind of similar to batch normalization. Well, it's not really batch normalization. They call it grad norm, and they basically try to normalize the gradients directly going like tagging the problem directly there in the layer where the layers where the different losses merge. And it seems to work, and they get good results. Probably in this world, but it's very recent work from a couple months ago. So that's one of the problems, but there are more problems. So another problem is that for some tasks you might have a lot of data to train on. For example, you're doing one of the tasks is image recognition, you have ImageNet, image classification, you have ImageNet, and the other task might be depth estimation, and the data sets for depth estimation that have actual values for the depth ground truth are very small in comparison to ImageNet. So they will not really be balanced. If you just train directly with that, probably ImageNet will train much faster, and then you will have again problems. One way to solve that is, okay, if you know that they are imbalanced, you sample more times from the data set that has less samples. And you have in each mini batch samples from each of the tasks in a way that they are kind of balanced. Also, there are challenges in the sense that if you're using these different data sets for different tasks, one data set might be for object detection in the street, and you have cars and bikes and signs and so on. But then you're having you're trying to your depth estimation task data set is for indoors, so the domain is completely different. Things like this, you can have problems. Or even if they are similar, they're not recorded with the same camera, things like that. So some people have tried to solve that doing some batch normalization for each task or instant normalization. And if you want to know more about this, you can ask the domain adaptation guys, because this is a very related problem. But you can also ask me, I don't know what.
I don't want to ask, because I'm not sure if I understood how you speak correctly, like the weight in the samples for each task. So like for within each batch, mini batch, you have like samples coming from
Different tasks.
So you mean that if the image classification data set is twice as big, for example, then you sample 2 images for the classification task and 1 image for that classification task.
Sorry. You just want to see the same amount of samples for each of the tasks. So you can do it in different ways, but it just maybe you see the same sample twice for one of the tasks, which is not optimal, but it's more optimal than just seeing less samples from that specific task than for other tasks. Right? And then the last problem is how to know which part of the network you want to share, what you don't want to share. So what belongs to the common part, they will train for that with gradients from all tasks, and what is specific to one of the tasks. And this is a problem that has been also studied for transfer learning, and there is no clear answer. But there are some insights that you can get from what has worked with transfer learning. So basically share your encoder as much as possible, and then just attach small parts to it. That seems to be the most reasonable thing. There is some more work on that direction. These cross-stitch networks use this approach. So they have 3 networks in parallel, and then they share features in between them, but they are 3 separate networks. So that doesn't really work for us, but it does work in the sense that it achieves better generalization. And one way to solve this would be, this trend of doing architecture search, so training models to find good architectures. You could apply this to find good architecture for multitask learning. I saw one very interesting work at here in Vancouver some weeks ago, which is kind of weird, even crazy. So you have a network like this one, and basically you share not only like in this axis, but also like this. So you can go first, see this part of the network, then see this one, then see this one. And it's kind of messy, but it also shares a lot of things and gets good results on MNIST. But something else in the future might be interesting.
How do you do many tasks?
Yeah, that's another thing. So there is a lot of people. I know there is a lot of people doing multitask learning or like investigating like stuff about multitask learning, and then they say, okay, each of the tasks is to predict this class. So predicting one class is one task. When it was defined multitask learning, it was defined with this idea. So multi-class problems are actually multitask problems for them. I was explaining it at a higher level, but Sebastian was saying it. He told me one day, multitask learning is more of a perspective, how you see problems, and it might be true. And most of the losses that we're using for one of the tasks, if you can break them down and have separate parts that are just sums of them, right? So is that multitask or not? But it's hard to say. But I'm talking at this higher level of perception tasks. But yeah, they analyzed it on this very simple data set of very related tasks. Okay, so I was gonna show some success stories. This is Ubernet, and they did 7 different tasks simultaneously at different levels of like detection, which is a high-level task, then saliency and surface normal, which are lower level. And as you can see, it works quite well. Then there was some work doing it on different tasks for face recognition. This was gender, and pose, and facial landmarks, and detection, random box around the face. And these guys got state of the art in, I think, 3 of the tasks they did. Then there is Maskar CNN, which does talk about multitask, but doesn't really do anything for multitask. The only thing they do is to put different losses together, and they do object detection and segmentation. And they also got state of the art on instant segmentation, which is kind of a merge problem, so makes sense. What else? So this is more related to what I was showing. So just to show what they did, an encoder, and then different decoders for each of the tasks. And the tasks were the classification of the road, the segmentation of the road, and detection of cars. And I think they also got state of the art on, or not state of the art, maybe. I think it was the first place in QT benchmark for segmentation of the roads. It looks quite good in that sense. And then there is a video. This is the one with actually caring about the weights in the losses. Right. It works.
The uncertainty is actually model.
Sorry?
What an uncertainty basically is model here.
I cannot tell you right now. Take a look at the paper. It's really good. So this was for vision, but it has also been used for other applications. For example, for machine translation. The first one is, okay, I have a language and I want to translate to multiple languages with the same model. And that's what these guys did. They got a lot of citations, so I guess it was good work. And then you can think, okay, but now I want also another language as an input. Do I need an extra model to translate to all these languages that I had before? Well, then Google came and they did this Google Neural Machine Translation, and basically they just trained with a lot of language pairs, just one big model, and that's extracts from their paper. They say improve quality, scaling up was presented a significant challenge. So it's kind of the same issues that we were having, I was talking about, but in this case, it's not for embedded devices. Well, it could also be, but I don't think this runs on the phones, probably runs on the cloud. But they were having problems scaling this up in the cloud too. So they came up with doing something like this. And as a byproduct of doing this, they managed to translate it in Japanese and Korean, which was a new like a language pair that the model had never seen. So kind of in a similar way to what these guys were talking about, there was some kind of shared representation here, which didn't really correspond to any language, and that allows for this translation from two different languages. So it encodes to this strange language in the middle, and then it decodes to a real language.
Did you say that translation from Japanese to Korean was better for this system than the other system?
No, I don't know. I don't think so. But it did learn to do it in a reasonable way because they were planning. So I don't know if it was the best one. So this is not only multitask learning, it's something else because you have different languages input. But it's, if you see it translated into different languages, multitask, it's really different. So it was just like a motivation. So, to recap, we have real-world problems which are actually solved with solving multiple perception tasks in many different applications, such as autonomous driving, augmented reality, so on. And I presented multitask learning, which scales really well with a number of tasks because we share is a common feature extractor, both during training and during test time. And this is essential for when you want to deploy in embedded applications or real-time applications. And as an extra, you have that if you do things properly, you will get a boost in performance by an improved generalization. And the good part, also, at least as a research point of view, is that there are a lot of unsolved challenges which are very interesting and that we can figure it out someday. That's it.
How do the training go? Do you simply alternate the data you send, training one perspective, like switching back?
So,
is there any science about how you send the data?
So what I did this. I studied this as a part of my thesis, my master thesis 1 year ago. And what I did was what I was telling before. In each mini batch, I had samples from all of the tasks that I wanted to train. And then whenever you had a sample that had no ground truth, that part of the network would have gradient 0, so it would not do any, it would not influence the training. But then every update of the weights would be done with signals coming from all the tasks because they are in the same mini batch. You could also have them in the same mini batch in the sense of a mini batch that you pass to the GPU, but you could just accumulate the gradients and merge together. Or even if you don't do that, it will shoot against one task, the other, but in the end, hopefully, it will average out. I don't know what's better, but something to study. So,
Yeah, I wanted to ask you that, if there is any multitask learning between different domains. For example, a way to train with speech and images from common models.
there is a paper called One Model to or One Network to Rule Them All that did something like that, and it managed to work. I don't think it was the best performing thing in the world, but it worked. So yeah, it had text and images. I don't know, something else. I don't really remember. But yeah, it somehow works too. Even if the tasks are not related or even the input is doesn't have the same format. So I don't really know what they did, but there is someone who had the same idea and actually did it.
How can you put L's and balls together? It's not possible.
I don't know. look at the paper. I cannot explain. Some other questions? All right. Thank you for coming, everyone.
So feel free to stay around for some time and mingle and talk to people. I'll close it.